Alright, in this video I'm going to be working Algebra 2 Quiz 7.2, which is about the fundamental theorem of algebra, which, just to remind you, is saying that the degree of the polynomial is equal to the total number of roots if you're counting multiplicity and complex numbers. Okay, so consider the third degree polynomial function f, which is x to the 3 minus 8x to the 2 plus 22x minus 20. It's known that f of 2 is 0, find all the roots of f. Okay, so we're going to start with that given root, and we're going to do a little bit of synthetic division. So 1x to the 3, negative 8x to the 2, positive 22x, and negative 20. And we're going to divide in, I may not have been enough room, but x equals 2. So 1, we're going to multiply 2, add that, multiply again, add, multiply, add, and get 0. Okay, that's good. Okay, we already knew that x equals 2 is a root. It's good to see that we did synthetic division right. Okay, now what we know is that we can factor f of x into x minus 2, because we just factored that out by dividing f by x minus 2, and we're left with 1x squared minus 6x and positive 10. Okay. And then we're going to factor that a little bit more, I think, by thinking to ourselves, are there two numbers that multiply to 10 and add to negative 6? No, there aren't. That's too bad. Okay, so we're going to have to use the quadratic formula. Okay, and so that was not going to get us anywhere. But, okay, we've got here x equals 2. But from over here, we can say x equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Okay, so I've got 6 plus or minus the square root of negative 4, all divided by 2. Okay, and then the square root of negative 4, that's going to be the square root of 4 is 2, times the square root of negative 1 is I. So I've got here 2i. And then I can divide both of these by 2, and I'll have 3 plus or minus I. So those are going to be all the roots of the polynomial f. Okay, this next one says the graph of polynomial p, which is 6th degree, is shown below. How many non-real complex roots does p have? Give a reason for my answer. Okay, well, there's 6 total roots. I see here a single root. See actually here another single root, but this one here looks like a double root. Well, I guess there's nothing here to say that it's not a quadruple root, and, I guess if you said this on the quiz and they marked you wrong, you could probably bring it back to me and say, if you said that there were no non-real complex roots because that was a quadruple root, I'm not sure why you'd think that, but, that's something that could be possible. I'm going to say that because I've got 2 singles and a double, that kind of adds up to 4, so it's a 6th degree polynomial. I'm going to have 2 imaginary. Okay, and the reason is, I think I'm just going to kind of show 2 imaginary plus 2 single roots plus 1 double root. That does add up to degree 6. Right. So that's going to kind of be my reason. That was something I saw somebody write on, a student write on a quiz when we were grading them. I thought I really liked that. This next one is find all the roots of this 5th degree polynomial, so we're expecting to find 5 of them, if we're including multiplicities and complex roots. And it looks potentially factorable because that 1 to 5 and 2 to 10 ratio seems constant, but I'm going to start by factoring out a greatest common factor. And if I want the roots of g, I want where g of x equals 0. Okay, so I'm going to have x to the 5 plus 5x to the 4, 2x to the 3, and 10x to the 2 equaling 0. I'm going to factor out x squared because I see that common to all the terms. And then I'm going to do some grouping factors. So x squared times, okay, out of the first 2, I see x squared in common, and I'm left with an x plus 5. And then from the second 2, just that 2. But I am left with an x plus 5, and that's a good sign. So we'll be able to factor that out and be left with an x squared, an x plus 5, and an x squared plus 2. Okay, so from all of these factors, this is as far as I can factor it, I'm going to have my zeros. So either x squared could equal 0. That would only happen when x equals 0. That's a double root. Okay, I could have x plus 5 equaling 0, and that would happen when x was negative 5. And that's going to be a single root, but I don't think I need to write that there. And then x squared plus 2 equals 0. That's something I'm going to need to do a little bit more work on. So I'm interested in solving the equation x squared plus 2 equals 0. And because this only has one power of x in it, I'm only seeing x squared. I'm going to be able to, solve directly for x. So I'm going to subtract 2 from both sides, take the square root, and when I take the square root of both sides of an equation, I need to remember that plus minus. Okay, and then I'm going to split this thing up like I usually do, but 2 isn't a perfect square, but it doesn't really matter. I'm going to have square root of 2 times the square root of negative 1. That's what we'd call square root of 2 times I. And so I'm going to report my other two solutions would be x equals square root of 2 times I, and x equals negative square root of 2 times I. Okay, and so, yeah, when I see 3 single roots and 1 double root, that adds up to 5. The g is a fifth degree polynomial. That makes sense. Okay, sketch the graph of y equals negative 2 times x minus 3 times x squared plus 4 in the space below. Okay, so the first thing is the degree. It's going to be a degree 3 polynomial because I see 1x here and then 2 more there. So that adds up to a total of 3 degrees. Okay, the leading coefficient is going to be negative 2, so I've got a negative leading coefficient, which means that the end behavior is going to look like y equals negative x cubed, like that. And so draw an x-axis. My zeros are going to happen when? Okay, negative 2, well, that can never equal 0. X minus 3, that could equal 0 if x was equal to 3. And x squared plus 4. Now, we learned recently that something like x squared plus 4, that could equal 0 when x was like an imaginary number. I'm trying to get a good straight x-axis, and that's probably as good as I'm going to get. So this is not going to contribute to any real solutions. Okay, but we do know that x equals 3 is a single root. So this graph is going to come from above, and it's going to, who knows, maybe it might have, like a little turning point. Oh, whoa, that was pretty bad. And we know that it needs to, somehow it needs to get steeper the farther I go to the right, so I might try that again. Who knows? But maybe it passes through confidently at 3, and then does its turnaround, like that. That could be possible. We don't really have the tools to know that yet. Okay, but we know that it's going to have one x-intercept, it's going to be at x equals 3, and it's going to be a single root, and it's going to have that end behavior. So that's about as good of a sketch as we can give. Alright, and the last two are just, give a sketch of a polynomial that has one positive root, one negative root, and 2 imaginary roots, and the other ones give a sketch of a polynomial that has one real root and 4 imaginary roots. Okay, I think the best way to start with these, think about the degree. So the degree is probably going to be, if they say one positive root, that's 1, a negative root, that's a second, and 2, so I'm thinking degree 4. Now you could get fancy and say, okay, maybe the positive root's a double root or a triple root or something, but that, just make it harder on yourself, so I don't see why you would do that. I'm going to say, all right, if it's degree 4 with 2 imaginary roots, it's going to have 2 real roots, right? Because they got to add up to 4. And the real roots, those are x-intercepts, and it can have up to, 4 arms to it, or 3 turning points, or 3 relative extrema, so you could draw it like that. 1 positive, 1 negative, that just means that the y-axis is going to have to happen somewhere between these x-intercepts. So, why not there? And there we've got ourselves a nice sketch of a graph that has those properties. And but you don't have to have those turning points. It could just look like a regular parabola if you wanted to draw it like that. I'll give a sketch of a polynomial that has 1 real root and 4 imaginary roots. Okay, so that would add up to degree 5. Okay, 1 and 4. Okay, so, you could draw like 1, 2, 3, 4, 5. like that, that would be good. But if you just kind of wanted to draw it, increasing from left to right, that would work. I think if it was going to have a double root, then, okay, then in behavior, the arms would have to point the same direction, but then that would add up to degree 6. Okay, but I think that's a good sketch, and that's what most of the people in my class gave. Right, now form B. I'm going to go a little faster through this one because the problems are all just the same with slightly different numbers. So it's known that f of 3 equals 0, find all the roots of f. So I'm going to do some synthetic division here. And divide by x minus 3. Because I know that they're telling me f of 3 equals 0. So I drop it down, add, multiply, add, multiply, add, sure enough, f of 3 equals 0. Okay, so what I've done is I've divided f by x minus 3 and got a clean quotient, so I know that I can write f as the product of x minus 3 and whatever I'm left with, x squared minus 4x plus 5. And this one, I think this is going to be one of those, this is one of those that it looks factorable, but it isn't, right? Because I would want positive 5 and positive 1, that adds to positive 6. Or I would want negative 5 and negative 1, and that adds to negative 6. Okay, this is not going to work. I would need minus 4x minus 5 would work. Okay, so, you can double check and make sure that you did your synthetic division right, but you did, and we're going to have to use the quadratic formula. So from the first factor, I know that f could equal 0 if x was equal to 3. But from the second factor, I'm going to use the quadratic formula. So I'm going to say x equals negative b plus or minus the square root of b squared minus 4 times 8 times c. So 16 minus 20, all divided by 2a. Okay, so this is 4 plus or minus the square root of negative 4, all divided by 2. The square root of negative 4 is going to be the square root of 4, which is 2, times the square root of negative 1, which is I. So I've got 4 plus or minus 2i divided by 2, and if I divide that whole thing in half, I'm going to divide both of them in half, and I'll have x equals 4 plus 2i, and x equals 4 minus 2i. Okay, and those are going to be all the roots of f. It's a third degree polynomial. I found 3 roots. I'm feeling good about that. The second one is telling me I've got an 8th degree polynomial. How many non-real complex roots do I have? Okay, well, I've got 2 single roots right here and 1 double root down here. So if I have 2 singles, 1 double, and some number of imaginaries, they have to add up to the degree of the polynomial. That's what we learned this time. And the double counts for 2, so I've got 4 already, and so I have 4 unaccounted for. Those are all going to be imaginary, and that's what I'm saying is going to be the number of complex roots. Okay, and I think that, and if you weren't watching Form A, what I said was, in my class, this was, we thought this was actually a really good reason, and we definitely gave credit for that as a reason. All right, so find all the roots of g. This one's factorable, yeah. So we see x to the third in common to all of them. That should probably catch your eye. And let's see what I'm left with. X to the third plus 2x squared plus 5x plus 10. This is looking factorable because that 1, 2, 5, 10 ratio. And if I'm looking for the roots of g, I'm going to set g equal to 0 and factor away. So do some group and factor here. Can factor out an x squared from the first 2 terms, and I'm left with an x plus 2. And then from the second 2 terms, I can factor out the 5. I'm left with another x plus 2. And that's still equal to 0. Okay, I can factor out an x plus 2, but that's x cubed times x plus 2 times x squared plus 5, and that's equal to 0. So, okay, now that I've got it fully factored, I'm ready to solve, right? So if any of the factors were equal to 0, the whole product of them would equal 0. And so if x cubed was equal to 0, that would only happened when x was equal to 0. Now that is going to be a triple root. X plus 2 could equal 0. That would be where x was equal to negative 2. And x squared plus 5 could equal 0, and I'm going to solve that one out. Okay, and I don't need to use a quadratic formula on this or try to factor because I just only have one power of x, so I can solve it that directly. And then I'm going to take the square root of both sides. Okay, and I'm going to have x equals plus or minus the square root of 5 times the square root of negative 1, which is I. Okay, and so I have two more. X equals root 5i and x equals negative root 5i. And between the triple root and 3 single roots, that does add up to degree 6, so I'm feeling good about that. Alright, now on the back side, we're just going to sketch some graphs. So this is going to be a third degree polynomial because I've got 1x here and 2 more there. It's going to have a negative leading coefficient because of that negative 3 out front. So degree is 3, leading coefficient is negative. So that means the end behavior is going to look like this, like y equals negative x cubed. And I'm going to draw an x-axis. I'm going to say, all right, the x-intercepts are going to be x equals 2. And that's going to be the only one because x squared plus 1, that would return me like an imaginary solution, or 2, actually. And so I know that it's going to come down. Maybe it goes like that. Yeah, we don't really have enough information to know if the turning points exist at all, or if they happen to the left of 2 or to the right of 2. But we do know there's going to be an x-intercept at x equals 2. We know it's a single root, so the graph's going to pass through confidently, and we know the end behavior, so we can sketch a pretty decent graph. And the last two problems are just 2 more sketches. So this one, I'm going to say, okay, 2 positive roots, 1 negative root, and 2 imaginary roots. That's a total of 5 roots, so I've got degree 5. Okay, I'm going to say, all right, 2 positive roots, 1 negative root, so that's a total of 3 real roots. 1, 2, 3, we could give it an extra couple of turns if we wanted to signify that it was degree 5, but that would be good enough. Okay, we would need to be careful about our placement of the y-axis to make sure that 2 of the x-intercepts were positive and only 1 was negative. So it would mean that we would have to put the x-axis, somewhere between the first 2 x-intercepts. But it didn't say anything about the leading coefficient, so yours could look upside down from this. It could have maybe, those 2 turns right there. Maybe you didn't draw those. That would be no big deal. We don't know that those are there. It's just conjecture. It could be, and still, that could correspond to the 2 imaginary roots. Alright, and then the last one is give a sketch of a polynomial that has 2 real roots and 4 imaginary roots, adding up to degree 6. Okay, but only 2 real roots, so 2 x-intercepts. 1, 2, 3, 4, 5. I'm going to need more x-axis here. Okay, that could be a sketch. You don't need to have the turning points, but you could not have more than that number of turning points and still have, unless you made the real roots like double roots or quadruple roots or something like that. Okay, so that's all for this quiz, and that's going to be all for this video. Thanks for watching.